Okay, this is chapter 5B. In 5A, we looked at interrupt. How do we implement an interrupt routine in a microcontroller? Now, we look at microcontrollers has got timers, and we look at how do we program a timer, how do we use the timer for various delays, or a timer can be used as a counter. So we looked at all sort of options available. Timers. And in the microcontroller, PIC microcontroller, there are 3 timers available. Timer 0, timer 1, timer 2. We will just look at timer 0 only, and then you can look at 1 and 2, you can look at the data sheet. Let me concentrate on timer 0. Now, TMR0 has a wide range of application in practice, and we can use the timer for time measurement, or we can program it such that the timer count external pulses coming in, and we want, for some application, we want to count how many pulses came through. And if we were to generate pulses of an arbitrary duration, we can use the timer as well. So there are 3 applications here I mentioned, and we look at one at a time. So time operation, when used as a timer, the timer 0 module can be used either as a 8-bit timer or an 8-bit counter. So that timer is, now we're going to look at 2 operations as an 8-bit counter and an 8-bit timer. And timer is, you will find that's in bank 0 and hexadecimal 1 location, you've got the timer register. And that's the register that we are going to use for loading a value into the register or counting a value from an external pulse coming into that particular register. We can configure the timer using the option register. If you look at this particular block schematic diagram, and this pin is the PA4 of port A, which can be programmed to cause interrupt, or can be, we have looked at that in the previous chapter. Now we can look at a pulse coming through. We want to count the pulses. We can count the pulses based on falling edge or rising edge. So option register has got this TOSC bit, and we can program that as a 1. If you put it as 1, then it's for rising edge. And the pulses goes through this one. And we set this up. 1 is for counting mode, 0 is for timer mode. So we want a counter mode. Pulses are coming through here, and we want this to be counter mode. It goes through this one. And then the pulses, the clock frequency can be changed. So you can actually divide the frequency. Well, if in a counter mode, you may not need to divide, but you can still divide them, and you can, depending on how you want it, you can set up a value here, and I'll provide you a table there, and then you can actually divide the clock frequency. Having said that, if you are counting pulses from here, then you don't need to use this at all. You just set this one, you don't enable this one, and it goes through this one into the counter. This is the 8-bit counter, and it just gets counted here. So we don't use the scaler for a counter. We will only use it for a timer. We want to time out, then we'll use for just simply for counting. This is not enabled. And then we have got another timer called Watchdog Timer, which is operational this way, and I'll show you that in a minute. So this is just an internal block diagram. You can program it such that you can operate as a counter or a particular timer. So let's look at how do we do that. So timing mode. We want an 8-bit timer, and which will increment, the timer register will increment for every instruction cycle. So we need to select the timer by clearing the TOCS bit 5 of the option register. So you go the option register, and that bit 5, and if you look at that bit is, if it is 0, then every instruction cycle, it works as a timer mode. It just counts. So that register is incremented. When used as an 8-bit counter, that means this pin should be enabled as a counter pin. So that means you need to go, you need to select that pin, which is in port A, and then you need to go into option register. TOSC bit need to be selected. So you can see that bit, you need to select them. If it is 1 mean increment on a high to low transition. If it is 0 means increment on a low to high transition. So you set that one here. Once you have selected that, then you are ready. This is set as a timer now. And we will look at small programs to see further. So remember, for timer mode, you need to look at option register. There are 2 bits which need to be selected appropriately. And if you go into the option register further, this one we have already looked at it before, pull-up register, enabled or disabled, and we don't need to worry about that now. Now we are going to look at 3 things. First one is a group of a scalar, selecting a particular value, the input clock frequency will be scaled, and then you got scalar assignment. So if you make PSA equal to 1, the scalar is assigned to a watchdog timer, which I will explain later on. It's a particular timer, they are free running timer. If you set that to 0, then your scalar is set up for timer 0 module. So what does that mean? What does timer 0 module mean? Okay. Now look at these 3 bits. So there should be altogether 8 options, 2 to the power 3. So if you set everything 0, 0, 0, 0, that's that position, then your timer clock frequency is divided by 2. And the watchdog timer clock is not changed. When you go for 0, 0, 1, your clock frequency is divided by 4. When you go all ones, your clock frequency is divided by 256. So it shows you that how the choice of frequency allows you frequency divisions of incoming clock signal. And that scale is useful because as soon as you reduce the clock frequency, your instruction time takes longer, or your timer acts as a delay unit, and which helps you to create various type of delays. So we are going to look at a timer on a counter mode. How are we going to do this? I'll do this as a question. A push button is connected to a PA, that's here. We need to program as an input port. And write an assembly lines program, continuously count the number of pulses. So every time you press this one, it should count the number of pulses. And when you press and release the button, 1 count, and continuously displays the counter value on the LEDs. So every time you press, release, this will increment, and the counter value. There are 8-bit counter. You may assume that this already have a switch debound circuit. So we are going to, here, this is where we are providing a pulse. And that goes here through this, and through this, come back, and we are going to count it. How do we do this one program? So to configure timer 0, we need to select the external input, which we know how to do it. TOCS option bit we need to select. And then we will count at a rising edge, so we need to set TOSC bit of the option register must be 0. That means it will count on that edge. So when you have a pulse, it will count on that edge. Then we do not want to prescaler. There's no prescaler, as we want to count the exact number of pulses. So we don't want the pulses to be delayed. Every time pulse comes, we want to count the number of pulses. So PA is SA of the option register should be 1. Once you have done that, these values do not matter. So once you have set this PSA is equal to 1, it will go through this one, but they won't affect. So whatever the frequency the pulses are coming, it will be counting the ones, 3 pulses in here. So let's look at the values. So what value we have to then, when we need to load them in the option register. You have to enable this one, so that's 1. You've got to enable that one for the positive edge, that's that one. Those are the 2, that and that bit done. Then the next one set to 1. Once you have set this one to 1, then this is not enabled. These are immaterial what value you have. That doesn't function. So that's why we have got this 101 here. We load this one into that register. Let's look at the program. How are we going to do this one? It's very simple. It's called event counting using timer 0. And I don't need to go through all of these. You've already done this bank select and then port A digital, then port B digital, and you just clear them, all of them. Bank shell Triche, and then you want to make sure that port B is an output port, and also, Triche, so port A, the pin 4 should be an input because that's where the clock frequency is coming. So we select that pin and PA4 and it's equal to 1. Then you go Triche and send that to the port, then clear B, all B ports are cleared, and select port B. Well, this means make all ports are output, and then select port B, and then clear port B directly. At the same time, timer is in the 01 hexadecimal register. That may have a value, maybe, may not, but for safe side, you clear the timer. Then you go to option register. In the option register, you have to tell you're going to use external edge, which is equal to 1, and no prescaler. So that's what the value we had. That's no prescaler. That's for rising edge, and you put the value into a W register and move that to the option register. Once you have done that, while you are there, select port A. You've got the port A selected. So all the initialization is done. Now all you need to do is move the timer register value. 0 means move the content into the W register. You move that into W register. Whatever timer value, the timer register value, that means this one, every time pulse comes, this goes 1, 0, initially 0, 0, 0, so it goes 0, 0, 0, 0, then 1, 0, 0, 0, then 1, 0, 0, and pulse counts are count. Every time you read that particular timer value and send them to the port. When you do that, this light will glow. It will glow according to the bit pattern and at the frequency of where the pulses are coming in. So it depends on how you press. So if you press fast, that should change faster. If you press slowly, that will change slowly. So every press like that as normal rate, maybe about 1 hertz, and you will see this one will be initially 0, then that glows, then a pattern comes in. And then you go back into the main program and loop. So that's an example of, and if you've already got your hardware with a hexadecimal display here, and you can then send it to that, and you can see number 1, 2, 3, 4 appearing. Number of pulses. So counting number of pulses is very important in many applications, right? And you use this timer. So previous example, the timer was used in counter mode. Now I'm going to switch the timer into timer mode. So that means you preset a value in the counter or in the timer memory, and you subtract them at a particular And when you do that, then it will act as when it reaches 0, there will be a flag set. Okay, let's have a look at it. Timer mode is selected by clearing the TOCS bit of the option register, bit 5. Earlier example we had as 1. 1 means it's a counter mode. This is a timer mode. In a timer mode, register increments every instruction cycle. So it increments, it doesn't decrement, it increments. Right? As 8-bit register, TMRO goes from 00 to FF. So maximum value 255. When it reaches the maximum value FF and is incremented further, it rolls over to 0. So you start with 00, hexadecimal 001, and dot 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 dot, and FF. And then if you increment further, it goes back, rolls over, and keep counting A. So the register overflow after FF, if you add 1, there will be an overflow, right? When you add them, there will be a 9th bit will be 1, and that is recorded in this particular bit, which is called the timer 0 interrupt flag bit. And if you check that bit, if it is 1, you know it's timeout has happened. So TOIF bit can trigger an interrupt, and if it's enabled. So if you enable an interrupt, you have an enable bit, you enable that, and when this goes after FF, this flag setting will cause an interrupt, as long as you enable the interrupt at the start of the program. So timer 0 interrupt is enabled by setting the TOIE bit. So where is TOIE bit will be is here. By setting the TOIE bit, and when the counter is then incrementing it, and when it reaches 00 after FF, this bit is set. This is the flag bit. Okay? So this is enabling. E stands for enabling, and the F stands for flag. But any enabling that you need to do for interrupt enable, there's a global interrupt enable bit there that need to be set as well. So you need to make sure that you set the GIE bit as well before you enable that. You enable that, then wait for the timer gives a flags, and you check this flag, and if that's 1, then timeout has happened. It has counted from 00 to FF. You may set up not 00, maybe at decimal value of 200, and it will go 200 to 255, and then timeout comes. Depends on what initial value you set up. You can start to set up count from here to here, or you can set it up here, and it can count from there to there, and then go back there as well. Well, it may not go back. It will go up here and then go back here, unless you set a value there. The interrupt would be an indication of timeout and will occur on every overflow of TMR register. So the question is, what is every overflow? So you started with 00 hexadecimal, count, FF, then count one more pulse, one more clock cycle or instruction cycle will make that to 00, flag bit is set, and then keep counting. While it's counting, you can do all sort of interrupt work, and you can clear them. Or you can stop counting while you are servicing the interrupt routine. So all it says is that once you enable the timer, when it reaches the maximum value, it gives you a flag bit. And using that flag, you go into interrupt service routine. And when you come out of the interrupt service routine, you must make sure this flag bit is cleared. Otherwise, when it comes out, it will go back again to the interrupt service routine if you don't clear it. It's important that. So that's timer mode. Let's look at how do you do the timer mode. Okay, well, just a little bit more on this. If the clock frequency of the PIC microcontroller 4 kHz instruction cycle is, divided by 4, so it will be 1 microsecond. So the counter would then be clocked every 1 microsecond. Okay. The clock is divided by 4, remember? 1 microsecond. That's called instruction cycle. Therefore, the timer 0 will take 256 microseconds to count from 0 to FF and then to 0. So, by preloading the TMR register with a suitable value, a smaller timer interval delay could be achieved. So, for example, if you load the TMR 0, which is H01 location, this is TMR. If you load that with the value of 200, then the timer overflow will only happen 256 microseconds for the full 00 to FF, minus 200 microsecond, because 200 value you have loaded, so okay, after 56 microseconds. An 8-bit programmable divider is also available. So remember here, you are operating the timer. Now timer can be slowed down. If you slow down, then the overflow will happen after a long time. And slowing down means you divide the clock frequency. So there's a prescaler divides the input frequency by one of 8 binary values. So we looked at the values. It can go from divide by 2, divide by 4, divide by 8, divide by, and it can divide by 256. So with the 1 megahertz instruction cycle, if you enable the prescaler, right, which I said to you earlier, PS0, PS1, PS2, by putting the appropriate value, and the lowest one is 256, you can get 65 millisecond delay. So if you want to go back and have a look, which slide I did it, is this slide. Do you see it under the timer mode? If you enable the timer and you select this value 111, then the instruction cycle is divided by 256. So it's first clock pulse first, and then divided by 256. The next one comes. So there's a delay of 65 milliseconds. That's what it shows. So you've been told you have to select these values. And then you can find out at what frequency it's going to come out. It depends on clock frequency divided by 4, which is the instruction frequency. Whatever the prescaler value you have set up, 256, 128, 64. And this is whatever timer value you put it in, divided by that. That's your frequency. And the timeout will occur 1 over F out. And you can actually do a calculation on that. So we are going to generate a 10 millisecond delay. You have done this before by just looping it. Now this, by just putting some instruction and looping it, you were able to get 10 milliseconds before. Now we are going to use the timer to get the 10 milliseconds. Now you can see if you preload the timer R0 with 100, decimal 100, and the overflow would occur after 156 microseconds. That is 256 minus 156, minus 100 microsecond here. Will give you 156 microsecond. And if you use a prescaler value of 64 instead of 128 or 250, you get a timer of 9.984 millisecond. You need another delay of 16 microseconds, 16 instruction cycles you need, which easily you can get them. And once you have that, you've got a full delay of 10 milliseconds. Remember, the option register has to be set up this value so that it will give you 64 prescaler. So we have enabled that, and then we have put 101 in there. And just move that back to the option register. And I'm just calling a delay routine, 10 millisecond delay routine. So you go to delay subroutine, where I say move my W register with 100 and move the value, W register value, into timer. Timers now has got 100 in it. It can go only up to 255. Now what I do is I go and look at my INT count second bit. So where is the second bit? This bit. That bit is the flag. I want to see whether that flag is set. That will be only set if the timeout happens. So I'm setting that. But remember, before you set all these interrupts need to be set up, and we will do in another question. So I'm setting up, and if that has not been set up, then I'll go back to loop and wait until it's being set up. Once it's set up, what I need to do, I need to clear that particular bit, because I'm going to go out of the program, and the next time I can come. So, and then it's return and go back to the main program. And you can do a 10 millisecond through this. You'll have a bit more than 10 milliseconds. Sorry, that one will give you almost 10 milliseconds, actually, if you do the calculation. So, that's how the timer is set up. Timers based delay. And you will find you do need to use the timer to get delays. Longer delays, if you want, you need to do the timer 1 and timer 2. They are 16-bit registers. Okay. But just do with the 8-bit register for the moment. Get the principle understood, and then for the project you can use the other ones. Now I'm going to use timer interrupts. So whenever there's a timer happen, then interrupt happens. I want to use it as an interrupt. And then earlier I didn't use it as an interrupt. The previous example, what I did is I'm just polling it. I'm just keep waiting it. I'm going back here, checking it and waiting it, checking it, and I didn't set it up as an interrupt. This flag will be set up, but I didn't set it as an interrupt. I'm only looking for that flag. If the flag is there, just timeout has happened. But now I want to do it as an interrupt. So how do I do it? Write the interrupt routine to increment the number of port A. When timer registers overflows, it causes an interrupt. So you are going to service an interrupt routine. And the maximum timer period is 65.53 milliseconds, corresponding to the prescaler value of 256. You know, when you have an interrupt-based program, when you run into the interrupt, you must save the W register and the status register. So you need to have these two instructions to make sure that you got, that should be moved here, that should be moved there. These two memory locations are reserved for interrupt. And all those things, these are assembler will look after. You come to your main program. I'm not going to go through the main program, how do you set port A, which you have done already, previous example. But I select the option register. Option register is here. And what do I need to do in the option register? I need to select the option register, and then I need to go clear the bit of 5, bit 5. So if I go and clear this bit, that means I've selected the timer mode. Not a counter mode, timer mode. Then I go to the same option register and then select bit 3. And I'm select bit 3 mean by setting this one, I've selected this scalar. Then I decided the prescaler value is 256. So I know from the table I looked at, I need to put 1, 1, 1 into this location. As soon as I done that, I've got 256 scalar selected. That means the instruction cycle frequency 1 megahertz will be divided by 256. I've done that. Then I go to the INT register. That is this one. Why? That's where I have to enable the interrupt. So how do I do that? First I go set the bit 5. 5 is this bit. That means the time T0 means timer 0 interrupt I is interrupt is enabled. So I've enabled that one. Then I go to bit 7. Bit 7 is the global interrupt enabled. All interrupt to, globally if you want to enable the interrupt, that's what you have to do. So you enable that as well. And then you clear port B. That means in the port B everything is 0. And then you just wait in a loop. You just keep waiting. So what happened now? Clock frequency comes in, divided by 4 is instruction cycle, 1 megahertz. That's divided by 256. So the frequency is 1 over, the period is going to be 1 microsecond divided by 256. and timer will be incremented by 1 every 1 over 256 microsecond. Okay? 1 microsecond divided by 256. So it's very slow. So when it's happening one after another, you have enabled all the global interrupt. As soon as a flag is set up, that will set up when your counter has read FF, and then when the next clock comes, it goes to 0, 0. As soon as that happens, that will be set to 1. As soon as it reaches FF, the next clock cycle, it'll be 1. It will be 1. As soon as that's 1, an interrupt is caused. So your program will leave here and go and serve the interrupt service routine. In the interrupt service routine, what do? Remember, I save my W register. We have done this one. I'm not going to go through this one. I save my W register and the status register. Then I select the port B, and I increment the port B by 1. That's what I have to do. Every time I cause an interrupt, I increment by 1. And then I select the interrupt count register, and I clear the interrupt flag bit. Remember interrupt flag bit? TOIF. It's here. I clear that. So I'm ready. I've cleared that. I've finished the interrupt. That's all interrupt is doing. It's a small interrupt, just to show you. And now then, you go back and put your register back into the W register and the status register. Status register you do first, and then these two instructions, remember we looked at it before, that will make sure that the status register bits are not changed by this operation. Because if you do other operation, there may be a 0, there may be a carry, there may be something can will upset the status register, and you may not have the same status register content at the time of arriving and at the time of leaving. You stored them in the memory. So you want to make sure this swapping instruction. Once you have done all of these, then you go back and then say, right, I'm going to enable the interrupt again. You have to enable the interrupt again. Once the interrupt is enabled and a flag is set up here, I think if you read it, this needs to be re-enabled again to use the interrupt. And you return from there to your main program. So that's how you do the timer. So timer thing, you can actually cleverly do that. Using this, you can actually increase your timing value to many seconds very easily. If you start to do timing through loops, small timings like in the order of millisecond is easy enough to do, but if you are going into hundreds of milliseconds, then timers are the best way to doing it. The last part of this section is Watchdog Timer. Remember, this is a timer always free running in the system. But the way it is set up that it will be running for 2 seconds and then automatically reset. So what happened? Why do you need this? Say you have a program and you wrote your program and it got into a loop. And your program had an error, it cannot get out of the loop. So it will keep running. So this particular timer, free running timer, after so many seconds, resets everything. If this timer is not there, it won't reset. And you're going to turn off the power to reset. Instead of that, this timer is built in. So one of the major functions of the Watchdog Timer is just looking at your program, looking at the function happening, but it doesn't know what's happening inside. But it makes sure after every so many seconds, it resets everything, you start from scratch. If you do not want that to happen in your program, you have got to reset that particular bit so that it will never automatically reset. So this Watchdog Timer built in there has its own oscillator. It has got its own oscillator, this Watchdog Timer. When you set it up in that Watchdog mode, it goes through this. Well, this one is the clock. Watchdog is this way. It has got its own timer, and the clock is fed in here through this and through this. You can feed here or you can feed it. Just look at the diagram with further detail. It's very hard to explain. Yeah, this will create a pulse, and it's just timeout will happen after so many seconds, right? Now we'll look at this. In the original table I showed you, the clock frequency is divided by, instruction cycle frequency is divided by 128. In this case, oscillator is to a clock frequency, divided by 4 is the instruction cycle divided by 128, maximum for a watchdog timer. Okay? And when the watchdog timer is enabled, the counter starts from 00 and incremented by 1 and reaches FF. When it goes to FF, and PIT microcontroller reset. Goes to FF and then go to 0, it will be reset. The only way we can stop this resetting is you periodically check in your program and you clear this watchdog timer using that particular command. Otherwise, it will run for so many seconds and then it will reset your program. You don't want that to happen. If the program does get stuck for some reason, this WDT timer will then reset the PIC microcontroller, causing out the program to restart from the beginning. So it's basically, you can see that is your main program is running, and in some way it got into the loop. It can't get out. It's running here, can't get out. But you have a watchdog timer, it's incrementing at a low frequency, and when it comes to FF goes to 00, it creates a flag, watchdog timer flag, that automatically tells, go back to the start, reset everything and start. And this is, if you don't want this to happen, in your program, you should always check this flag bit and reset the flag bit, then to start again and keep counting. It's a good function to have. And you may ask, you may ask me how it is set up and what sort of frequency it is operating in. A frequency, you can set it up at 128, divide by 128 is the prescaler value. Prescaler is not readable or writable. You can't read or writable. When assigned to the timer module, instruction writing register will clear the prescaler. When the prescaler is assigned to WT, a clear instruction will clear the prescaler as well, along with the WT. When changing prescaler from a timer to the WT module or vice versa, care must be taken. Well, you can look at the instruction set which shows. I'm not going to go into detail here too much because, you need to be aware of it if you are writing a program on a microprocessor level. You need to be aware of it. We have set it up here, the prescaler at the internal frequencies. Every 2.3 seconds, it will reset. And you will find most of the program will run less than 2.3 seconds quickly in a microcontroller application. Therefore, this won't be an issue. But it's an issue if your program gets stuck. Then after 2.3 seconds, just after 3, it will reset the whole lot. So it's a facility available, watchdog timer, which you need to enable them in a real application. You need to enable them. Now we come back to the last part of the program, which is the last activity, activity 8. This is the last lab that you'll be doing. After that you start on a project. There'll be more lectures recorded, but they are purely for usage in the project as opposed to as a lab activity. In this lab activity, you can see that same as what you had before. It's a one switch here, like a lab activity 7, and you count the you press, and it says that when you press this button, right, connected to when it's closed, assuming that an intruder coming into the house, a 1 second timeout must be implemented. As soon as you press it, a 1 second timeout should be implemented. That is 1 second timeout. It was 0 timer when it stayed for 1 second, like a like a monostable multivibrator. You give a pulse, it can last for one second using the appropriate RC value. And then what you need to do at that position, at RC node, you need to provide a pulse like that for the 1 second. If it's a duty cycle of 50% duty cycle. And that goes in here, and the buzzer you can get from the stores downstairs. When it is 1, this transistor is biased, so it's conducting, and this will be connected to here. When it is 0, this is not biased, so this is not connected. So what is fed here will be, for the buzzer, is a inverted high and low, like that. Same frequency comes out, and you will find the buzzer will buzz at that frequency. You don't need, you could have a lamp instead of a buzzer. Buzzers have their own oscillators sometimes. You could do a lamp and lamp oscillating and flashing when that's happened. And the flashing should occur for 1 second. And also in this program that you need to do an interrupt, because as soon as you have your time output, then it should stop. Yeah, there should be interrupt service routine you should have as well. And when you write the interrupt service routine, you should look at the service routine and count the number of instructions you have, and then convert them into number of bytes needed, and then calculate how much memory space you need for the interrupt service routine. You should be able to do that without any problem. You will have always a machine code followed by the data. So we have looked at that in the very first slide, and it's a very good exercise for you to do. Take the interrupt service routine. You've got all the instruction written. Your program is working. Now you take the instruction and look at each instruction, say how many bytes each instruction consists of, and then calculate the total number of bytes, and then work out what's the memory space. That completes that particular chapter. Again, I've used these references to do this. So you should complete this laboratory activity 8 as soon as possible. Thank you.